Welcome to G Fun Facts Online. Today we are diving deep into the center of our planet to discuss a phenomenon that has recently upended geology, the inner core backtracking. For decades, the standard model of our planet's interior dynamics was relatively settled. Beneath the shifting crust and the churning mantle, the Earth's inner core, a Pluto-sized ball of solid iron, was thought to be spinning independently. It was believed to be super-rotating, spinning slightly faster than the rest of the planet. It was viewed as a planet within a planet, driven by magnetic torques and governed by its own distinct rhythm. However, that rhythm has changed. In a cascade of groundbreaking studies published between 2023 and 2025, seismologists have challenged this long-held consensus. The inner core has not only slowed down, but it has also effectively paused and begun to spin in the opposite direction relative to the mantle. This phenomenon is known as backtracking or subrotation. This deceleration of Earth's heart is not a catastrophic braking event, but part of a massive, multi-decadal oscillation that has profound implications for the length of our days, the stability of our magnetic field, and our understanding of planetary formation. To understand the significance of the backtracking discovery, we must first look at the history of the inner core itself. It is the most inaccessible region of our planet, buried beneath 3,000 miles of rock and molten metal. In the early 20th century, scientists believed Earth's core was entirely liquid. It was the Danish seismologist Inge Lehmann who, in 1936, shattered this assumption. While analyzing seismograms from an earthquake in New Zealand, she noticed faint primary pressure waves, or P waves, arriving in a shadow zone where no waves should have been able to penetrate if the core were purely liquid. Lehmann proposed a radical solution, suggesting a solid inner core was reflecting and refracting these waves. This boundary, now known as the Lehmann discontinuity, marked the discovery of the inner core. It was established as a solid sphere of iron-nickel alloy, growing slowly over billions of years as the liquid outer core cools and crystallizes. This crystallization process releases the latent heat that drives the Earth's magnetic dynamo. For 60 years after Lehmann's discovery, the inner core was treated mostly as a static object. Then, in 1996, geophysicists Xiaodong Song and Paul Richards published a landmark paper in Nature. By analyzing decades of seismic waves passing through the core, they observed that the travel times of these waves were changing systematically over years. Their conclusion was startling. They proposed that the inner core was rotating faster than the mantle and crust. They estimated this super-rotation to be about 1 degree per year. This meant that every few centuries, the inner core would make an extra full revolution compared to the surface. This super-rotation hypothesis became the dominant paradigm, portraying the inner core as a dynamic engine spinning ahead of the pack. However, the consensus on super-rotation began to crack in the early 2020s. As datasets grew longer and computer modeling became more sophisticated, the steady super-rotation model stopped fitting the observations. In January 2023, Yi Yang and Xiaodong Song published a study in Nature Geoscience that sent shockwaves through the community. They analyzed repeating earthquakes, which are seismic events that occur in the exact same location years apart. They found that in the 1990s and early 2000s, the seismic waves from these repeating quakes showed clear temporal changes, confirming the core was moving. But around 2009, these changes disappeared. The seismic waveforms from repeating quakes became identical, implying the inner core had paused its differential rotation relative to the mantle. Even more intriguingly, data from after 2010 suggested the rotation had restarted, but in the opposite direction. While the 2023 study was highly suggestive, the debate was settled in June 2024, when John Vidal and Wei Wang published a definitive study in Nature titled Inner Core Backtracking by Seismic Waveform Change Reversals. Vidal and Wang utilized a highly specific dataset. They focused on 121 repeating earthquakes generated in the South Sandwich Islands between 1991 and 2023. They also integrated precise data from Soviet, French, and American nuclear tests from 1971 to 1974. They analyzed the specific seismic phase that travels through the mantle, outer core, and through the inner core, known as PKIKP waves, comparing them to waves that just grazed the surface or reflected off it. The study provided unambiguous evidence that the inner core's rotation relative to the mantle follows a predictable, oscillating cycle. From the 1970s to the early 2000s, the inner core was super-rotating, spinning faster than the mantle. Around 2008, the super-rotation slowed to a halt. The core became locked in sync with the mantle. From 2008 to 2023, the inner core began sub-rotating, spinning slower than the mantle. Relative to an observer on Earth's surface, the inner core appears to be moving backward, or backtracking. Vidal stated that the inner core had slowed down for the first time in many decades, providing the most convincing resolution to the debate. The question then becomes, why would a solid ball of iron the size of Pluto stop and reverse direction? The answer lies in a titanic tug-of-war between two fundamental forces of planetary physics: electromagnetism and gravity. The Earth's outer core is a turbulent ocean of molten iron. As it churns via convection, it generates the Earth's magnetic field. Because the inner core is metallic and conductive, the magnetic field lines grip it. As the fluid outer core flows, it exerts a magnetic torque on the inner core, attempting to spin it. This is the accelerator, generally responsible for the super-rotation. Opposing this is the gravitational torque. If the inner core were a perfect sphere and the mantle were a uniform shell, the magnetic torque would spin the core unchecked. However, neither is perfect. The Earth's mantle has density anomalies, huge heavy blobs of rock deep underground, and the inner core is also not perfectly uniform. These density irregularities create a gravitational lock. The massive, dense regions of the mantle exert a gravitational pull on the dense regions of the inner core, trying to align them. This gravitational coupling acts as a brake or restoring force. When the magnetic torque spins the inner core too far out of alignment, gravity pulls it back. The interaction between these two forces creates a massive harmonic oscillator, essentially a planetary pendulum. In phase 1, the magnetic torque spins the inner core forward. In phase 2, gravity fights back, slowing the rotation until it stops, which corresponds to the pause seen around 2008. In phase 3, gravity pulls the core back toward equilibrium, causing it to spin slower than the mantle, leading to the backtracking we see today. The recent data confirms this cycle takes approximately 70 years. Just as the scientific community was digesting the confirmation of backtracking, a new study in early 2025 added a layer of complexity. Published in Nature Geoscience by Vidal, Wang, and colleagues, this research revealed that the inner core is not just spinning, it is deforming. While the 70-year oscillation model fit the long-term data well, there were still tiny, jagged irregularities in the seismic record that pure rotation couldn't explain. The 2025 study introduced a shocking solution. The surface of the inner core is not a rigid solid like a steel ball bearing. Instead, it is soft enough to be molded by the turbulent pressures of the fluid outer core. The fluid outer core, swirling with hurricanes of molten iron, hammers the surface of the inner core. This pressure causes the terrain of the inner core to shift and flow over timescales as short as a single year. Valleys and hills on the inner core's surface can grow or shrink. This viscous deformation means that the inner core is shape-shifting. When seismologists see a change in a wave's travel time, it is not just because the core moved. but because the core looks different than it did a year ago. This finding paints a picture of an inner core that is dynamic, soft, and constantly being sculpted by the fiery ocean surrounding it. To measure these movements, scientists rely on earthquake doublets. Every earthquake sends out a unique fingerprint of waves. Occasionally, tectonic plates will snap in the exact same spot with the exact same mechanism years apart. These pairs are called doublets or multiplets. Waves that travel only through the mantle look identical, proving the source is the same. However, waves that dive deep and pierce the inner core show differences. If the wave from an earthquake in 1998 arrives a fraction of a second faster than a wave from 2024, it means the path through the inner core has changed. In the 2024 study, researchers saw that between 2003 and 2008, the waveform differences increased steadily, indicating the core was rotating away. But between 2008 and 2023, the differences began to decrease and eventually matched the old patterns. This is like a spinning carousel. If the horse moves forward, you know it is spinning. If it moves back to its original position, you know it reversed. The seismograms showed the inner core reoccupying its old position relative to the mantle, which is definitive proof of backtracking. The slowing and reversing of the inner core has real-world effects on the surface. The first is the length of day. According to the law of conservation of angular momentum, if the core slows down, the mantle and crust must speed up slightly to compensate. The backtracking of the inner core contributes to a shortening of the length of day. We are talking about fractions of a millisecond, but atomic clocks are precise enough to measure this. The recent trend of the Earth rotating slightly faster correlates remarkably well with the inner core's deceleration phase that began around 2008. The second implication involves the magnetic field. The inner core is the battery of the geodynamo. The 70-year cycle of the inner core matches known fluctuations in the strength and direction of the magnetic field. Sudden, sharp changes in the magnetic field, known as geomagnetic jerks, often align with changes in the inner core's rotation regime. Finally, the validation of the 70-year cycle confirms that the Earth's interior is tightly coupled. The gravitational lock between the mantle and inner core is strong, implying that the density anomalies in the mantle are dense enough to physically yank the inner core back, influencing the planet's rotation as a whole. The inner core backtracking phenomenon transforms our view of the Earth's center, from a static ball of iron into a dynamic, oscillating, shape-shifting heart that dances to a 70-year rhythm. From Ing Lehmann's shadow zones to the analysis of nuclear echoes, we have peeled back the layers of the planet to reveal a mechanism of staggering complexity. As we move through the 2020s, we are witnessing the backswing of a planetary pendulum. It is a reminder that the solid Earth beneath our feet is anything but still. It is alive with motion, governed by the deep, silent physics of the core. Thanks for listening to G Fun Facts Online.